To continue on here, lecturing on equilibrium. Then we're going to roll into next chapter, the last on bases. So last time we spent pretty much the entire period there talking about solving equilibrium problems using ice tables. And we did ice tables as we talked about ICE, initial. And again, if you're given just sort of the initial concentration of your reactants, then you could use your molarities and assume that your product side there is 0 to begin with. Remember the change part, if we're assuming it is going to the product side, would be minus x's and plus x's. We also want to use the coefficients to make sure we take care of the stoichiometry part of it, the mole-to-mole relationship. And when we get down, we just bring everybody down. And as we talked about, basically this goes into your equilibrium expression and you solve for x. Now we saw a few different ways to solve some of these problems. Again, you may have to use a quadratic formula like we did in a couple of examples. And remember again that you will get 2 answers when you do this. And out of those sort of 2 answers that you get, one of them will not make sense when you kind of put it back into your equilibrium line. You usually will lead yourself to a negative value for the concentration, and you can't have obviously a negative value for the concentration. Remember also that you can get really any combination of x values. You could get 2 positives, 2 negatives, a positive and a negative. So you may want to have to check some of them depending on sort of the x values that you do get. Once you do that, you do put the x values back into the equilibrium line. That will then give you the equilibrium concentrations of everybody. And you can check yourself like we talked about again by just simply putting those values back into the equilibrium expression. And with rounding, you should get pretty close to what the equilibrium constant value was. So if you're really, really far off, if you do that at the end of a calculation, probably something went wrong with your calculation along the way. So it's a really good one, especially if you find yourself maybe doing the quadratic at the end, lay it back into your expression and make sure that everything at least appears to be correct. Yeah. Again, any sort of combination of x values you get, 2 positives, 2 negatives, positive, negative, at some point, one of those x values, when you put it into the equilibrium line, will give you a negative number, just the math of it when you put it in there. So, for example, you may have a positive value that is larger than the initial concentration, so that would give you a negative. Other questions? All right, so in addition, we also talked about, obviously, if it's sort of a perfect square, we did one of those, I think, where you could just kind of square root both sides and it makes it a little bit easier. We also talked about another important sort of way that we could solve these problems, especially if the equilibrium constant value is small. So as we talked about, if the equilibrium constant value is small, that obviously means that when we reach equilibrium, we mainly have reactants present. And in those situations, you can assume that x is equal to 0 in that case. Again, the idea there is because the equilibrium constant value is so small, we would expect the change to be relatively small as well and negligible. So you could try to assume that x is equal to 0. Remember that you can't really get rid of all the x's, otherwise you have nothing to solve for. But really the ones we're talking about in most situations are when you look at your table or even your expression there, are the ones where you're basically subtracting x from a number or even adding x to a number are the ones that you want to do. So those are the ones you want to zero out. Typically speaking, if you just have x by itself or 2x or something of that nature, where you're not really subtracting x from a number and it's sort of started at 0 like this guy did, even though the change is going to be relatively small starting at 0, any change is going to be significant. So obviously, in addition to not allowing us to solve the problem, we can't zero that one out either. So you should have one that you have left over. When we do make an assumption and you do solve and get the x value, You do need to check your assumption. It will not always be correct per se. And again, we're going to use the 5% rule. So once again, the way that you check your assumption is you take the X value that you got and you divide it by really the initial concentration and times it by 100%. And again, if it's like 5% or less, you're good to go. You can go with the assumption that you did. If it is more than 5%, you typically need to go back and solve it some other way. And as we talked about last time, that probably is going to be a quadratic sort of way to go back and solve it. The last thing is, although we did it in molarity, we also did an example with pressure, so it works the same way. Remember, though, that when you do it with pressures, it does need to be in atmospheres when it goes into the ice table. Even if it may be asking for some other unit, you got to put in an atmospheres, do the calculation, and then take it out. Any questions on any of that stuff there that we talked about last time? Okay, then let's talk about sort of the last part of this chapter, which is Le Chatelier's principle. And Le Chatelier's principle is really the idea of we have a system at equilibrium. So we have this nice system at equilibrium, which basically means, as we've been talking about, that the rate of the forward direction will equal the rate of the reverse direction. So when we do have this system at equilibrium, we do something to stress the system. And basically what that does is when we add a stress to the system, it, for the lack of a better word, messes up this equilibrium. So by adding the stress, it will then really kind of screw the equilibrium up. You no longer will have really kind of back and forth at the same rate. So what the reaction is going to want to do is try to get itself back to a state of equilibrium. And in order to do that, usually one of three things will occur. It will try to get itself back to equilibrium by shifting to the right, is sometimes referred to. And shifting to the right means that we are obviously making more products. It will sometimes shift to the left to try to get back to equilibrium, which means we would be making more reactants. And lastly, even though you may add some type of stress to the system, it may actually not do anything. So there is actually a few situations where there will actually be no change, even though you might have done something to the system. You will actually see kind of no change occur. So what are some stresses that we could deal with? We could deal with concentration, so either adding more or removing. We could deal with pressure and volume when we're dealing with gases, so those are common ones. We could also do something to the temperature, which will affect the equilibrium. Lastly, we could add a catalyst, as we'll talk about. Really won't do very much. But these are some of the ways that we could have a system at equilibrium and really do something to it that will sort of mess it up. So let's start with concentration and sort of talk about how that works. So if we do something to the concentration in a system that's at equilibrium, there really is kind of two things that we could do. So in terms of concentration, we could either add more or we could remove. So those are really the two things that we could do to a system that's at equilibrium. To add more, what happens when we add more, it will actually shift away from the side you added it to, which means if you add more reactants, it will go towards the products. If you add more products, it will go toward the reactants. It will go in opposite ways. And when we remove, it will actually go towards the side you removed it from. Now, when we talk about sort of sides in Le Chatelier's principle, there clearly is, like, if you have this in a beaker or a test tube, there's like no left side or right side in the test tube or the beaker. Everybody's in there swimming around. Some reactants, some products are basically in that beaker or whatever it may be. So when we talk about left side, right side, we're also talking about the balance equation that's happening. So either more reactants or more products is sort of what we're looking at. So for example, if we had a system that was at equilibrium, we'll do advanced stick figures. That's the ones with the faces here. There we go. We'll call this guy on the left our reactants, this guy on the right our products. And this system we'll say is at equilibrium, right? So if we decided in this case that we wanted to add more products, so somebody hops on the right-hand side here, what's going to happen in this case now is we're going to get this situation occurring. Right. And now clearly we're no longer at equilibrium. Now, in order to fix this problem, do I need to put more people on the left or more people on the right? Yeah, so to fix this problem, we added to the right-hand side. So to fix it, we need to kind of shift to the left-hand side and really put more people on the left-hand side. And when we do that, we will return back to equilibrium here. And remember that when we do return back to equilibrium, we're referring to the rates of the forward and reverse direction will once again basically equal each other. And we're back to our second equilibrium position at this point. So when we add more products, we would expect it to shift to the reactant side. If we add more reactants, we would expect it to shift to the product side. Question on that there. Now, let's say we have the same sort of equilibrium set up here. And let's say, again, this is our reactant side. This is our product side. Let's say this guy hops off. And when he hops off, this deal is going to happen. At this point, we would need more people on the left, more people on the right. We need more people to go onto the right-hand side. So we remove from the product side at the right. It will shift towards the right to fill like the hole, if you want to think about it that way. And once again, we will come back to equilibrium position here and be happy afterwards. So when you add more reactants or products, what you're really doing is making that reaction sort of happen. So if you add more products are there to react, which means the reverse direction is going to happen. If you add more reactants are present, which means the forward direction is going to occur, and that's why it shifts in that direction. When you remove products, it will come towards the product side. You can kind of think of it like a hole. So it's going to try to get back there and kind of fill that hole back in. Same idea on the reactant side. If you remove some reactants, it will shift towards it. Any questions on that there? Now, when we're dealing with gases, we do talk about pressure and volume, and oftentimes they're tied together when we are dealing with gases. And there is a gas law that relates both pressure and volume, and that gas law is our good friend Boyle's. Yes. P1 V1 equals P2 V2. When the pressure goes up, what happens to the volume? It does go down, right? Which is why the pressure goes up, right? Gas molecules are in a smaller area, increases the number of collisions. And vice versa, if the pressure goes down, we would expect the volume to go up. Larger volume gives everybody a lot more room to fly around in, and that means less collisions and the pressure goes down. So when we do have the pressure increasing and the volume starts to decrease, the sort of change that's going to happen is because the volume is coming down, pressure is going up. So to kind of fix the pressure going up, would we need more or less gas molecules in the smaller volume? So once again, the pressure went up was the change, right? So kind of bring it back to equilibrium and bring it back down. Would more gas molecules or less gas molecules in that smaller volume do that? less gas molecules. Yeah, so smaller volume, we would need less gas molecules. That will bring the pressure back down, less collisions. So it will shift to the side with the least number of gas molecules. Now, obviously, that is reaction dependent as to which side has the most gas molecules. You would have to look at the equation and frankly count up anybody that has a G next to it, right? And the coefficient, and see which side has basically more or less. Now, if they actually have the same number of gas molecules, that would be a situation where you would get a no change that would occur. There is really no more or less in that situation. So that is possible to occur. Now, if the pressure goes down, we would expect the volume to go up. So again, in this situation, sort of the change that's happening is when we mess up the equilibrium, we're going to see the pressure start to drop. So we do want to kind of bring the pressure back up. Now, in order to bring the pressure back up in a larger volume, we would need more gas molecules to fill that larger volume. So it would shift to the side with more gas molecules. And once again, that would be dependent on obviously the equation that you're looking at. I personally usually like to look at this one in terms of volume, and it's pretty simple. Small volume, less, and larger volume, more gas molecules. So it's a really easy way to relate it. As long as you understand the relationship between pressure and volume, you know, a lot of times just thinking about the volume aspect of it is sort of the easier way. Any questions on that there? So let's see here if I got all right, so for each of these things, will it shift to the right? Will it shift to the left? Or will there be no change? Let's say here we added some C, we removed A, we increased the pressure, we increased the volume here. All right, so take a moment based on this reaction, which way we expect things to shift as a result. Is a product, that means we're going to have more products, and really what that's going to do, right, is kick off the reverse reaction. So it should shift away from where we added it, so we should expect it to shift to the left in this case. If we remove A, so A is over here on our reactant side, so in this case we're going to remove reactants, which means really in this case we're going to end up having more products and kind of like a hole on the reactant side. So that's going to cause it to actually shift towards the side we removed it to. So it should shift to the left. Any questions on those two? Here we're going to increase the pressure. When we increase the pressure, that means really the volume starts to decrease. And that means we should look for the side that has the least number of gas molecules to sort of counteract the rise in pressure that we got. We want to bring it back down. So again, simply just looking at the coefficients, that's 3, that's 1. So that is 4 gas molecules on the left, and that is 3 gas molecules on the right. That means in this case, it should shift to the right-hand side as it has the least number of gas molecules. And lastly here, if we increase the volume, we would expect the pressure to come down. So again, to sort of counteract the pressure coming down in that larger volume, we would need more gas molecules to have more collisions to bring the pressure sort of back up, if you will. And that means in this case, it would shift to the left. Any questions on any of those there? Okay, so yeah. When we remove A, what really happens is you can think about it one, two ways. Sometimes I like to think about it as you kind of removed A, so there's like a hole there, right? So the system, right, is constantly kind of going in both directions. So as you remove A, right, it kind of creates a deficiency or a hole on A on the reactant side. And really what that means is you really have kind of more products at that point, right? And that means really the products are going to be able to react a lot easier with each other because of the availability of it. And that's going to cause really the reverse reaction to come. and that's going to bring back really your reactant side sort of back up to kind of finish it. So sometimes I like to think of removing it as like, okay, I made a hole on that side, I could go fill it. So it's going to kind of go towards the hole to fill it. And again, the opposite is true when we add. Basically, when we do add, it just basically promotes whichever side we added it to that direction to occur because of the availability of the reactions or products being there. Other questions? Speaking of which, talking about adding and obviously removing. Adding either a reactant or product is pretty simple, right? You just kind of go to the shelf, grab the reagent and dump it into your beaker or whatever it may be. How do we sort of remove something? Do we just reach into the beaker and grab it out? That would be no, that is the wrong answer. Don't reach into the beaker ever. Yes. By the way, if we have an aqueous solution, right? What really is an aqueous solution? What's really floating around in there? So like if I have a sodium chloride solution, what's floating around? Yeah, so in most cases in a solution, you pretty much have like ions floating around, right? That's basically they're aqueous, they're floating around in there. So one way that we could remove something is if we add something to our beaker or our test tube that maybe creates a precipitate, right? So you got these things floating around, you add something that kind of grabs them out of solution and drops them into the solid phase, right? As a solid, based on solubility rules and stuff like that. Now that is essentially like reaching in there, right, and grabbing out those, say, ions out of solution and removing it. And now that it's in the solid state, right, the two things that don't really participate in equilibrium, pure liquids and solids. So again, that's like removing it. So that's one really common way that you can remove something from, say, a reaction is to add another reagent that may cause a precipitate to form. And again, that would be either, depending on which side it is, either reaching in and grabbing something off the reactant side or grabbing off the product side, depending on which side it actually reacts with. Another way that you could do and remove something that might not be as visual that you could see it, obviously you'd be able to see the solids being formed, is actually the formation of water, right? So water is a pure liquid, and this works really well when you have reactions that has either hydroxide or H plus or H3O plus, whatever you want to call it, in the reaction. And that is because basically H plus and OH minus is water when you put it together. So if you have H plus in a reaction, you add some strong base, which is a source of hydroxide, OH minus. It will essentially go in there and grab up the H plus. That will make it water, which is a liquid and not participate in the equilibrium. And again, that's essentially going in there and grabbing out the H plus, and vice versa. If you had some equilibrium that had hydroxide, OH minus in it, you could add some type of acid, right? Basically what makes something an acid is it has an H plus. So by adding the acid, the H plus will go find the OH minus and they will come together to make water. And again, that would be essentially like removing the OH minus. Again, visually, you might not be able to see that you made water, but there might be some other things that you'll be able to see to know that it went one way or the other. So those are two very common ways in a sort of Le Chatelier's principle that you could kind of remove something, add something that makes a solid, or add something that forms water. Any questions on that there? Okay. So the next really important thing that can affect equilibrium is temperature. And temperature basically works the same way as concentration, which means if we increase the temperature, it will shift away. And if we decrease the temperature, it will shift towards it. So what determines sort of which way that will be? It really is the type of reaction that we're dealing with. And when we talk about energy, perhaps you're familiar with, they did take a lot of energy out of the previous class. But when we talk about energy, there's really two types of reactions. There are exothermic reactions. And exothermic reactions basically is when heat or energy is released. And there are endothermic reactions. And that was when energy is absorbed. So there's really kind of two ways that energy is basically displayed in a chemical equation or reaction. And most of the time it's displayed as a delta H value. Delta H is the change in enthalpy. We'll talk about it when we go backwards in the book. But enthalpy is basically the heat of a reaction. And if the reaction is exothermic, the delta H value will be a negative value. Vice versa, for endothermic, the change in energy will be a positive value. So for the most part, if you're dealing with energy, if it's a positive number, it's usually an endothermic sort of process occurring. And in general, if you're dealing with energy and say negative number, it's an exothermic process that's basically occurring. I would say probably 9 times out of 10, that is probably how energy will be displayed to you in most of the cases, because it's chapter 12 and they assume you went through that energy chapter in the first semester, which obviously we did not. So you'll most likely see the equation written at the end. They'll say delta H is equal to negative or positive. The actual number doesn't really matter. It's really just the sign, negative or positive, that does matter in this particular case. The way that we think about exothermic reactions, and because heat is being given off or released, we oftentimes think of heat or energy as a product. So heat and energy is a product. Not correct 100%, but that is how we think of it in an exothermic sort of reaction. And in an endothermic reaction, we think of heat and energy as a reactant, like it's being absorbed or being added to. So that means if our reaction is exothermic and I increase the temperature by putting my test tubes in some hot water like you'll do today, and we shift to the left, we would expect it to shift to the left away from the product side, and vice versa. If I decide to put I decided to put my test tubes on ice, that would be like removing heat and energy. And in the case of an exothermic reaction, we would expect it to actually shift towards the product side. So it works exactly like concentration. Add, it shifts away, AA. And if you remove it, will go towards it. Vice versa for endothermic, if I increase the temperature of an endothermic reaction, we would expect it to shift away from the reactive side towards the products, and vice versa. If we put it there into some ice and remove the energy, we would expect it to go towards the reactant side. So in terms of determining whether it's exothermic or endothermic, we can use just simple hot water, cold water, basically, or ice water to determine that. Any questions on temperature here? The last thing that could affect an equilibrium is a catalyst, and a catalyst is, again, not a reactant. It is not a product, and it does not get used up. So it does not get used up in a reaction. It is typically there to really facilitate the reaction occurring faster. In most cases, that is what people are talking about with a catalyst. There are negative catalysts that actually slow down a reaction, but most of the time, a catalyst is there to speed up a reaction. A lot of times you can find catalysts, on top of the arrows, and in a lot of cases, if you add a catalyst, there will actually be no change. So it will get to equilibrium quicker, but there will be kind of no change that will occur. So that's one very common way that you can get no change. Another common way is you add something like, say, a noble gas. Noble gases are chemically inert, which means they're not going to really do much. So they won't affect equilibrium. So that's another way. Any questions on that? Now, as you might remember, the only thing that will actually change the value of the equilibrium constant, right, is the temperature, right? So the temperature is the only thing that will change the actual value that you have for the equilibrium constant. So let's say we had something like this. All right, so what will happen here, once again, to the right, to the left, or no change. All right, let's say I add a catalyst. Let's say I add B. Let's say I decrease the temperature. Let's say if I increase the pressure. Let's say if I remove C. Let's say if I increase the temperature. All right, so take a second to and decide which way we're going to shift in this case. No change. Yeah, so again, you'll get to equilibrium a little quicker probably, but it really won't cause a change to occur. If we add B, so we're going to add B. So when we add, it goes away. So B is a reactant. So we would expect it to shift to the right-hand side in this case. If we decrease the temperature of this particular reaction, is it exothermic or endothermic? It is endothermic because of the positive sign. That means that basically heat is a reactant. So when we decrease the temperature, that'll be like removing heat or energy, and that should create a hole on the left-hand side that it wants to fill. So it would go to the left-hand side in this case. If I increase the pressure, that means the volume again will go down. And in this case, if we have a smaller volume, we would definitely want less gas molecules. So grand total gas molecules on this side is 5, and this side is 6, based on the coefficients. So we're going to head to the left-hand side in this case. Any question on those so far? We're going to remove C, which is a product. So again, going to kind of create the hole on the product side we need to fill. So it should come towards that side. So it will shift to the right. In this case, we're going to increase the temperature, and we already determined it is endothermic. So increasing the temperature would be like adding more reactants, and that will kick off really the forward direction of this reaction. And we would expect it to go to the right. Questions on any of those there? Question on Le Chatelier's principle. All right, so we kind of talked about these, but so we'll kind of go through this here. Again, concentration, shift away if you add, go towards if you remove. Once again, the temperature being the only thing that changes the astronumerical value, important to determine whether it's exothermic or endothermic as to which way it will shift. And obviously pressure of an inert gas won't affect it. So again, if you have some type of noble gas, it won't do much. But again, looking at the volume, smaller volume, less gas molecules, larger volume, more gas molecules. All right, so we got this guy here. So let's just say the delta H here is negative 333. Why not? All right, let's go with increase the volume, add NH3, increase the temperature, and let's go with remove N2. Which way? All right, let's take a look. So in this case, we have increased the volume. That would expect the pressure to come down. In this case, in the larger volume, we actually need more gas molecules. Left-hand side here is 4 gas molecules. Right-hand side is 2, which means in this reaction, it should shift to the left. If I add NH3, again, adding products, going to add away, so it will shift to the left-hand side in this case. In this case, our delta H value is negative, which means it is a exothermic reaction. That means that heat and energy is considered a product. So if I increase the temperature, that would be like adding more products, which again means we should shift away from the side we added it to, and it would go to the left. And in this case, removing N2 would create a hole that we would want to shift here to the left. Any questions on that there? All right, let's take a look at this one here. And actually, we're going to get rid of this here for a second. We're going to pretend it's not that. All right, we're going to also pretend that there's going to be colors in these gases here. So we're going to pretend this side is red, and we're going to pretend this side is yellow. Yeah. So if your reaction goes to the right-hand side and becomes more yellow, if this reaction kind of heads to the left-hand side, it's going to be more red. So in this case, what would happen? Would we expect red or yellow if we added O2, if we added NO, if we removed O2, if we decrease the pressure? And I also want to know, is this reaction exothermic? Don't go by what was written there, or endothermic, based on what we see. So this is the first thing we did. We added we'll pretend there's a test tube that they're in. So we added the test tube to ice. And what we saw occur was it became more yellow. And we then added a test tube to hot water, and it became more red. All right, so based on those information, and again, we'll make believe that this is more aqueous here. So we'll make believe these guys are aqueous. Well, actually, we'll still pretend they're gas, but we'll pretend that there's color, so you'll see. All right, let's take a look. So first off, if we add more O2, O2 is a reactant, which means we should expect the test tube to become more red or more yellow. Which one? It should become more yellow. So when we add O2, it should cause the forward direction to occur. It should shift away. And that means that our test tube should turn more yellow in this case, right? That's how we would know, obviously, it's shifted to the right-hand side in this make-believe example. If I added more NO, it should cause the equilibrium to shift to the right, to the left. Should cause it to shift to the left, which means we should see more red, right? It should turn more red. If we remove O2, it should come towards the O2, right, as we create a hole. And that means we would expect it to turn more red as well. If I decrease the pressure, that means really my volume has increased, which means it should shift to the side that has more gas molecules. And in this particular case, which side is that? It is neither. It's a tie in this case, right? There's two gas molecules over here. There's two over here. So really there would be no change. And in this example, it would probably stay the orange color, right? At this point, it wouldn't really go in either direction. So that's another way that you could get kind of a no change, kind of a tie on both sides in terms of the number of gas molecules, and then you get no change. All right, so based on our observations here, when we added it to ice, capitalize it because we're doing ice tables, but regular ice, it became more yellow. And when I added it to hot water, it became more red. Would that be exothermic or endothermic? So let's reason through this, shall we? So if I added more ice, that means that it became more yellow, which meant that it had to shift to the right-hand side, right? Based on that first observation. When I added hot water, it actually went to the left-hand side, right? It became more red. So because temperature works the same way as concentration, in order for it to go to the right-hand side when we remove it, that means temperature has to be on which side of the arrow? When we remove something, it goes towards it. So that means that heat has to be on the right-hand side to make it come towards it when we lower the temperature. When we add temperature or heat, right, it goes away from it. So in order for it to go away from it, that means the heat also needs to be on the right-hand side. They actually agree with each other, yeah? And that's because the heat's on the right-hand side. That would make this, in my made-up example, an exothermic reaction. So based on what we saw, even though it may not seem like they both agree with each other, since one went one way, one went the other way, they do agree with each other that in order for both of those things to occur, the heat and energy has to be on the product side. Question on that there. You'll do more of that later in lab, I think, yeah. All right, question on Le Chatelier's principle. Obviously, you need to be able to do all that stuff. Yes, shift to the right, shift to the left. Okay, that should wrap up this chapter. As we talked about last time, we're going to quiz it up on Tuesday of next week at the beginning of lecture on this chapter. I know I'm looking forward to it as well. So off chapter 13, which is, I hope, acid and bases. So we're going to get into acid and bases. There's kind of two parts to the chapter, kind of basic sort of acid and base chemistry. And then we'll get into some weak acids and weak bases and how to handle those. So first off, an acid, hiding behind the orange there. Acids have a sour taste. Don't taste any acids in lab. But we do taste acids, obviously the citric acid, vinegar, which is acetic acid, is the main component of vinegar, as you might remember from your titrations. Acids react with certain metals to produce hydrogen gas in a single replacement reaction, as you also might be familiar with. HCl is hydrochloric acid. Zinc comes in, kicks out the hydrogen. That produces hydrogen gas, and in this case makes some zinc chloride as it comes together, a little 2 to balance it up there. And that's a single replacement one. Also, acids react with carbonates to form carbon dioxide gas. So if you take something like hydrochloric acid and react it with something like a little sodium carbonate, you will basically get a double displacement reaction that will occur. These two guys will switch partners. And the result of that is you will make some sodium chloride and you'll make some H2CO3, which is carbonic acid. That carbonic acid will then very quickly decompose into CO2 and water. Yeah, so like the plop, plop, fizz, fizz type of thing, which you get with some Alka-Seltzer. So you'll make those bubbles really quickly. Guess should also balance it, something like that, maybe. Now, bases, on the other hand, they feel slippery. Many soaps are bases, drain cleaners, things like that. Bases, a lot of strong bases. Have hydroxide in them. So things like sodium hydroxide, potassium hydroxide, a lot of those in group 1 and 2 on the periodic table are strong bases, kind of starting with sodium to potassium, and go right to calcium, and then up and down there is a lot of the strong bases will actually have hydroxide in them. Again, that is why they're called the alkali metals and the alkaline earth metals. The word alkaline means basic. Yeah, so somebody says make something alkaline, that means to make it basic. And a lot of our strong bases do come from them. They're named like normal. I'm sure we remember how to name acids, but just in case, we'll do our Cliff Note version of acid nomenclature, so you'll know how to properly name them, I hope. When you name acids, right, first off, what makes something an acid is it has H plus as its cation, right? And that is basically what names an acid. When we deal with acid, it really all involves whether or not there is oxygen. So it's all really about the oxygen. And if the answer is no, there is no oxygen, your acid starts with hydro something ic acid. And that is like HCl. That Cl is chloride, so this becomes hydrochloric acid. HBr, hydrobromic acid. Yeah. Now, if your acid does contain oxygen. It most likely will contain one of those polyatomic ions, and also maybe be called an oxyacid because it contains oxygen. If you remember, everybody's favorite things, polyatomic ions end in one of two ways, either ate usually or ite in most cases. And depending on whichever way your polyatomic ion ends, if it is ate, your acid will be something-ic acid, like HNO3. That is nitrate. So this becomes nitric acid, right? And if your polyatomic ion ends in ite, your acid will be something OUS acid and something like HNO2. That's nitrite. This would be nitrous acid. Question on naming acids. Hopefully that sounds familiar to you. I hope. Yes. Okay, so you definitely should know how to name acids. Also, right, you know, if there's a polyatomic ion that has a prefix or something in it, that is perchlorate, right? So that is perchloric acid, right? So you still keep the per in there. By the way, I write aqueous nested acids because that is typically what you do, because in order for it to be an acid, it's got to be swimming around in a solution, basically. And that means that it should be aqueous. And that is why we call this hydrochloric acid, why we call this hydrogen chloride gas, right? That's hydrogen chloride. So the aqueous part of it's really important because, again, that's basically your definition of an acid, is the ability to release that H plus in solution. Any questions on that there? All right, sorry for the 200-day flashback, but it happens occasionally. All right. So as we talked about, really, the first sort of definition of acid and bases came from Arrhenius. He did a lot of work with electrolytes, and he defined an acid as a substance that's able to produce H plus or H3O plus ions in water or solution. H plus is the hydrogen ion. Bless you. It is also sometimes referred to as a proton because hydrogen has one proton. It has one electron. How many neutrons does hydrogen have? It has none. Yeah, so hydrogen only has a proton and an electron, which in order for you to become positive, you need to lose an electron, right? Which leaves it just a proton. So in acid-base chemistry, H plus is oftentimes referred to as a proton. H3O plus is the hydronium ion. It is a polyatomic ion. For all intents purposes, anywhere H plus is written, you could write H3O plus. Yeah. We'll talk about really sort of the difference, why we get both for the one versus the other. But in both formulas, reactions, you could basically substitute H plus for H3O plus. Personally, I roll with H plus most of the time, but I know books like H3O plus, so they kind of roll with that one. Really, the main reason or way that you get the H plus versus the H3O plus is it's just a matter of how you would write your equation. For example, what we see here, this is really just hydrochloric acid in water, basically, sort of dissolving in water. And in this reaction, it has the water in it. And basically what's going to happen is this guy is going to kind of toss his H plus over to the water, and that would generate H3O plus and the Cl minus. You could just as easily write this acid, because it's a strong acid, breaking apart just like this, where you just call it H plus and Cl minus. And again, this H plus and that H3O plus are going to be equivalent to each other. So in the bottom one, I didn't put the water in, so I didn't get H3O plus. I just got the H plus coming off. But if you do want to include the water, you can, and you will get H3O plus versus that. The definition of a base is something that has the ability to produce hydroxide in water or solution. So for example, here, NH3 will actually take an H plus there from the water. The result of that is it will actually generate OH minus, which is why it's a base. NH3 is actually a weak base. Hence the arrows heading in both directions, a reversible sort of reaction. It is still considered a base because, frankly, it could produce hydroxide, but it is not anywhere near as strong a base as something like sodium hydroxide, which frankly is just has its hydroxide on it. When sodium hydroxide basically goes for a swim, it's going to 100% break apart into sodium ions and hydroxide ions, and going to be able to generate a lot of hydroxide ions really quickly, which is why it's a strong base. Strong acids, strong bases, as we'll talk about here, are really strong electrolytes, and that means that when they are in solution, they 100% break apart. Pretty much none of the whole units are together, and they just break all apart. Weak acid and weak bases, they are weak electrolytes, which means they really do kind of stay together, but they both are able to produce either H plus if we're talking about a weak acid, or OH minus if we're talking about a weak base. So they're able to produce those things, so they're still considered an acid or a base. Now, that was a really good sort of definition of an acid and a base, but he did a lot of work with really one type of bases, which are the ones that contain a hydroxide. Sort of a general definition of acid and bases is the Bronsted-Lowry. I don't know why his name gets left off all the time. The Bronsted-Lowry acid and base definition. The Bronsted-Lowry acid is a proton donor, so that is something that will give away a H plus, while a Bronsted-Lowry base is a proton acceptor. So once again, that is something that will accept the H plus. So in the case of the NH3 example here, the NH3 would be a base because what is happening is the water is actually donating the H plus over to the NH3. That means that the water is actually going to become an acid, and the NH3 here will be the base. The consequence of sort of the Bronsted-Lowry definition of acid and base is we create some pairs on the product side that pair up with the reactant. So there are two things that are sort of related to each other on opposite sides of the arrow. And in this particular case, the NH3 over here, which is the base, is related to the conjugate acid on the other side, and that would be the NH4 plus. So those two guys are related to each other. Base on the left-hand side, its partner on the other side is a conjugate acid, while water here is acting as an acid, and its partner on the other side is the conjugate base, which in this case is the hydroxide. So the relationship between those two things, either the base and the conjugate acid or the acid and the conjugate base, the absolute only difference that you could have between those two things to make them related to each other is one H plus only. So the only difference has to be one H plus, and that's what we see as we go from NH3 to NH4 plus. It gains one H plus as it's come in this way, and the water, which is the acid, will actually lose an H plus as it heads in that direction. The H plus that one gained and one lost is the same H plus. It's the one that was transferred from the acid to the base. So acid conjugate base pairs, again, the only difference that there should be is, again, one H plus difference. If there's anything other than an H plus difference, they are not related to each other. They are not considered conjugate base pairs. If you have more than one H plus, you have some other element that's different, they would not be related to each other. Any questions on that there? All right, so let's take a look at each of these. So for each of these, decide, are these guys conjugate acid base pairs? Pair. We have basically HCl and we have OCl minus or ClO minus, whichever way you want to look at it. Are they pairs? The difference between these two is an H plus, but they also a difference of this guy's got oxygen, this one does not. So they would not be a pair. So this would definitely not be a pair. How about H2SO4 and SO4 2 minus? Are those guys pairs? The answer is they are not pairs because the difference here is 2 H pluses. So obviously more than one. And if it is more than one, it cannot be a pair. So that guy would not be a pair, even though they are kind of from each other. They are not pairs. We'll talk about that in just a second. How about NH4 plus and NH3? They are, again, you could figure it out whichever way you want to do it. You could either put an H plus on that and you get NH4 plus, or take an H plus off the guy on the left and you get that guy. So that is a winner, that one there. H3O plus and OH minus. They are not. Again, the difference here is 2 H pluses, so that is too many. And then clearly none would be wrong in this case. Any questions on that there? So you may be wondering, well, aren't these two related to each other? And they are, but they're not related to each other in the sense of a conjugate acid-base pair. H2SO4 is what is referred to as a diprotic acid. Diprotic means it gives away 2 protons. Di2, protic means protons, so it has the ability to give away 2 protons. The H pluses actually come off one at a time, so they actually don't both just drop off. They actually do come off in sort of a stepwise fashion. So really the first thing that happens is the H2SO4 will drop off an H plus and have HSO4 minus. The next step is that HSO4 minus will really lay up an H plus and our SO4 2 minus. So when we look at really what's happening here, we'll talk about, which one's easier or harder, but this guy, which is sulfuric acid, and this guy here, the difference between those two guys is 1 H plus, and those two would be pairs. This guy right here, the HSO4 minus, and the sulfate, the difference between these two guys would also be 1 H plus, and they would be pairs. But going from the H2SO4 directly to this guy, that's like a 2-step process, and it's too many in a row there, and they would not be pairs. So they are derived from each other, but the actual one that kind of ties both of them together is the HSO4 minus, which is able to go either way. Any questions on that? By the way, would it be easier to take off the first H plus or the second one? The first one's much easier. It's something that's neutral, right? And when you release the H plus, you now have HSO4 minus, which has a negative charge, and you want to rip something that's positive away from that. It makes it a little bit more difficult to do. So it is a little bit harder to do that. Any questions on that there? All right, so for this one, what would be the conjugate acid for this particular one? Starting with this guy here, what would be its conjugate acid? All right, so when you have something like this, it's good to think about the relationship that we talked about, an acid and base. On the left-hand side, our conjugate acid and our conjugate base on the right-hand side. By the way, that is how it goes. Your regular acid and bases are always found on the left-hand side of the arrow. Your conjugate acid and bases are found on the right-hand side of the arrow, and that's always how it goes. Our acid on this side should be related to the conjugate base, or our base is related to the conjugate acid. So if you're not sure what you're dealing with, you want to write the conjugate acid, which means, okay, I'm writing the conjugate acid. That means I am looking at a base, and the Bronsted-Lowry definition of a base is something that will accept an H plus. You should know that's the only thing you should do, either put it on or take it off, which is usually the hard part of it. So in this case, we would want to add an H plus to it by thinking about it that way. And we would get something like C6H5 NH3 plus. And looks like maybe it's number 2 there would work. So sometimes it's helpful to think about what is given to you because they won't always tell you it's a base or an acid, but they'll just say, you know, write the conjugate acid or write the conjugate base to this. So if you think sort of backwards, is it an acid or base? Then you just have to use the definition of the Bronsted Lowry to either put the H plus on or take it off. Any questions on that there? All right, we'll lay it up there for today.